This video covers multimodal language models. These are models that allow you to interact with both text and images. In particular, I'll take you through the LLaVA model, which is open source, and I'll show you how to fine-tune it on a custom dataset. I'll start off with a very quick demo of how a multimodal language model works, comparing it with the ChatGPT version. I'll talk a bit about applications where this is useful and why I think so many people will be interested in fine-tuning this kind of model. Then I'll talk through how these models work. They're the combination of a vision model and a text model that are adapted to work together. I'll cover three specific architectures: LLaVA 1.5, LLaVA 1.6, and IDEFICS, which is an earlier multimodal model that is based on the Flamingo architecture. I'll then prepare a fine-tuning dataset. We're going to be training a model on chess pieces. So I want the model to be able to recognize different combinations of wooden chess pieces after I fine-tuned it to recognize individual chess pieces. Then I'll show you a specific fine-tuning task on LLaVA 1.6. I'll do it on the one that's based on Mistral 7B and also a larger, more performant one based on Yi 35B, which is a 34 billion parameter language model. And as usual, I'll finish off with some final thoughts. We'll dive right in with some examples. Here I am on the demo page for the LLaVA model. This is available at lava.hliu.cc. And you can check out the most performant of these models, which is based on the 34 billion parameter Yi language model. So here I've uploaded an image, and you can see it's an image of a horse or a knight and a rook. So a black knight and a white rook. And I've asked the model, what do you see in this picture? And the model says, the image shows two chess pieces on a wooden surface. I'll just increase the font. On the left is a rook, which is a piece that can move straight line horizontally or vertically. And on the right is a pawn, which is a piece that moves forward one square at a time. Now, I don't know if it's referring to this here, which I think is actually a pawn, but really it should be calling out the knight here, which it seems to be completely missing. Then the answer goes on. The chess pieces appear to be made of wood, and the lighting suggests maybe taking a room with natural light coming in from the left side. So you can see that certainly it's on topic, knowing about chess. It gets the rook, but it doesn't quite get the knight. And this is roughly representative of the performance today of this open source vision model. Now, the private models like GPT-4 are more performant. When we ask the exact same question here, what do you see in this picture? ChatGPT says the image shows two chess pieces on a wooden surface. The one on the left is a dark brown knight, represented by a horse's head and neck. And the one on the right is lighter colored rook, which is the distinct cylindrical shape with a notched top that resembles a castle battlement. So GPT here is getting this answer correct. Now, even with ChatGPT, you can push the limits. For example, I've put in this photograph of a full chessboard, and I've asked the model, is there anything out of place in this image? And if you take a closer look, everything is in place except on the white side. The queen is not on her white square. So the king and the queen are in the wrong positions here. So here's what ChatGPT says. There's a chessboard with a full black and white pieces arranged. The white queen appears to be placed on a square that is not correct for the starting position of the game. So kind of recognizing what's wrong, but getting the wrong square. H5 is this square out here in the middle of the board on the side. So that's not the square where the queen is. And if we read on, the queen should start the game on square D1. That's always the correct starting square for the white queen. And additionally, the black king and queen seem to be placed in the opposite squares of their usual starting positions. And that's incorrect because the black king and queen are actually on the correct squares for their starting point. So you can see that GPT-4 is stronger here, the vision version, but still making some mistakes in interpreting this complicated chess image. Now, what I'm going to do after describing how these models work is fine-tune on a data set of chess pieces. I'm not going to get the model to perform at this level here of getting all the positions right on the board, but instead what I'm going to do is I'm going to take a series of photos of individual chess pieces, use that as training data, and then ask the model to answer what a set of chess pieces, what they see in a set. So I might give 2 pieces or 3 pieces and ask the model, which pieces do you see here? The reason why there are such powerful applications for vision and text models is because they can be used so widely. For example, you could think of fine-tuning these models for medical applications where you are looking at images and you're trying to detect patterns, issues, problems, healthy behaviors. You could use it for taking photographs of cars and seeing what kind of damage has been done and assessing the value of the repair, the cost of repair based on the images. There are almost endless applications. And by combining a language model with a vision model, which is what this video is all about, we can get a very powerful and interactive tool for diagnosing issues if we have a good training data set. Here we have one slide that's showing you how these vision and text models work. They're the combination of a vision model and a language model. In very simple terms, we have two forms of inputs. We have image pixels. So these are just individual pixels of an image. And we have input text in the form of phrases or sentences. So the image pixels come into a vision encoder, and through the vision encoder, they're converted into a set of vectors. And these vectors represent the meaning of what's within that picture. And the input text, meanwhile, is also converted into a series of vectors. And those vectors combined with the image vectors go through the language model. So basically, we're taking a language model, which would normally just be this right-hand side of my screen as I see it. And what we're doing is we're additionally putting in vectors that represent the image. So we have both image vectors coming in and we have input text coming in, and we use that combination in order to predict the next token. So you can see that really one side of this slide is just like how a transformer-based language model works, except now we've additionally added in some vectors for the images. Now, if we go one step deeper here, just to give you more granularity on the input text size, actually the input is sentences and words, and those words are chopped into subword tokens. So for example, the word token might be split into tok, T-O-K, or tok, and then N-E-N. So these subwords are actually the representation we take for the input text. And when we have these subwords made up of a vocabulary, often there might be, say, 32,000, a vocab size of 32,000. So just as we have 26 letters in the English language, you could come up with a vocabulary of subwords that's got 32,000 of those such subwords. Those subwords are then converted into vectors. So the meaning of each subword is represented by a vector in a very high dimensional space, not just 2D as you can see here, but maybe 1,000 dimensions or 2,000 dimensions. And these vectors, each of which represent a token, they're converted by embeddings. So embeddings are the matrices that we will multiply the inputs by, the tokens, in order to convert them into vectors. So to summarize, we have words, they're converted to subtokens, and these subtokens, multiplying their digital representations by embedding matrices, get converted into vectors. And so we have the text that's converted into input vectors, and these input vectors are what go into our language model. And on the left-hand side, we have pixels. They go into an encoder, which I'll talk about in a moment. And that encoder provides output vectors, which represent the images. And these vectors then are fed in parallel, just as we feed in text embeddings. And as an output of this language model, I previously said we predict a next token. Well, that's true. But more specifically, we predict an output vector. And that output vector is then decoded back. So we reverse the embedding to get back from an output vector into a representation of the most likely next token. So let's dig in on the vision encoder side. So I want to talk a bit about how we get from image pixels to vectors here. And the way we do that is usually by splitting the image up into patches. So here you can see this image of a dog, and I've split it in 4 patches. Often we'll have patches of 16 by 16 pixels, or patches or tiles. So this has 4 tiles. And each of the tiles, we take the pixels. So here in the red tile, we would take all of these pixels, say 16 by 16, and we would put them through some matrices, so multiply them by some matrices to get from pixels to vectors. So we'll have a vector that represents this tile. So you can think of this kind of like embeddings in the same way that we would go from tokens for words or subwords into vectors, we go from these tiles or patches into a vector that represents the patch. So this image would have 4 vectors, 1, 2, 3, 4. And these are trainable, by the way. So the matrices that convert the pixels within this red patch into a vector, these are trainable matrices that are trained through backpropagation. So anyway, we've got 4 vectors now, and these are the vectors that are fed into our vision encoder. And the vision encoder itself is a multi-layer neural net, and it makes use of attention. So it's architected in the same way that transformer language models are architected. We have feed-forward layers. We have attention layers. So typically in a block, there's a feed-forward and an attention layer. And then we repeat that block many times, maybe 12 times. And what this does is it takes the input vectors and it basically moves them and makes them interact such that we have an output representation that captures well the meaning of what's in the image. So the role of this whole block here is to start with image pixels in red, green, and blue. Each pixel has got a certain amount of red, a certain amount of green, a certain amount of blue. That's how you represent the color of the pixel. You also tack on a position. So you would put a position for each of these patches. And once you've got the positions and the pixels, you're going to take that and generate a vector. And that vector then will be representative of the pixels and the positions. And these vectors then go through the vision encoder and they generate an output, which is representative of the overall image. So here's a slightly different representation, just so you can wrap your head around the entire architecture. So now I'm going back to show you the entire vision plus text model. Here on the left-hand side, you can think of having 2 image vectors. So these can represent 2 of the tiles on an image. And then we have some text vectors. Maybe say and then hello. So maybe this represents the word say and this represents hello. So we feed in the image vectors and the text vectors, and then we make a prediction for the next token based on paying attention to all of these previous tokens here, or rather all of these previous vectors here. So the information from the image and the text all gets fed in to make a prediction of the next token, or rather the next vector, which gets converted to the next token. Now there's one more step that I have to show here that's needed if you're going to combine a pre-trained language model, for example, LLaMA, with a pre-trained vision encoder. So one of the key hacks with these vision plus text models is instead of training everything from scratch, we take an off-the-shelf language model, we take an off-the-shelf vision encoder, and we see if we can make them work together. And the way we do that is by realizing that the vision encoder will provide some output vectors. So it'll provide a vector for effectively each tile of the image. And the language model is expecting input vectors. Now it's used to receiving these input vectors that come from embedding the text, because that's what LLaMA was pre-trained to do. So these vectors it's very accustomed to, but it's not going to be accustomed to the output vectors of the vision encoder because these are trained on disparate data sets. So they're not compatible per se. So to make the language model compatible with the vision encoder, what we do is add in an adapter here. And this adapter here is also just a series of trainable matrices, and it converts, or rather makes compatible the output vectors from the vision encoder with input vectors of the language model. And there are a few ways to train this adapter that we're going to see right now. So let me talk about LLaVA 1.5, which is the precursor to LLaVA 1.6. This is one of the more recent open source vision plus text models, and it makes use of a clip encoder plus a LLaMA 2 language model. So they're the 2 building blocks it uses. And it then freezes the vision encoder and the language model and just trains the adapter. So to show you that, the LLaVA 1.5, it will take the vision encoder, it will take the language model, although LLaMA 2, it will freeze those weights, and then it will just train this adapter here. And it will train it using text and image pairs. So there are data sets available of images that have captions. So LLaVA 1.5, it will train this adapter. In other words, make the vision encoder and the language model compatible with each other. And it will do that by freezing the vision encoder and language model and just training the weights in this adapter here. So that's step 2. And then step 3 is for LLaVA 1.5, everything will be unfrozen. So make everything trainable, including the language model, including the vision encoder, including the adapter. And then use synthetic image plus text data in order to fine tune the model. So the synthetic data is instruct data. It's got kind of like question answer format, which is great because that encourages the model to perform well when we ask question and answer when we have question and answer style conversations. And the way that LLaVA generates this data is actually using ChatGPT. Now, don't confuse that with thinking LLaVA is trained using the vision version of ChatGPT. It's not. It actually uses GPT-4, which is a language-only model, and it uses that to write detailed descriptions of images given details of their contents. So basically, there are data sets out there of images, and the image has got some bounding boxes at different positions for each object in the image, and that object is labeled. So if you have an image and it has labeled objects at certain positions, you can feed that into GPT-4 and get out a detailed description about what's in the image. So that's roughly how LLaVA is making synthetic data, and it works well because it allows you to get this very natural question and answer style format, engaging the image within a text conversation. Now, LLaVA 1.5 has been superseded by LLaVA 1.6, which has a couple of tweaks. So one basic way you can improve these models is just start off with better building blocks. So instead of using, say, Llama 2, you use Mistral. Or instead of using an earlier version of CLIP, you use a later version of CLIP or a bigger version of CLIP. So LLaVA 1.6 does this in 2 ways. First of all, it uses Mistral 7B and also uses Yi34B for a larger version. So these are larger and more powerful models than the base Llama 2 7B model. And also LLaVA 1.6 uses a larger vision model. So it uses a 336 by 336 pixel image input compared to a 224 by 224 image input. So these are the first changes with 1.6, just better initial building blocks is one way to put it. And the second improvement is around the adapter. So in the first case, in LLaVA 1.5, the adapter is just a set of linear layer. It's just a linear layer rather. In LLaVA 1.5, the adapter is a linear layer. So it's a single layer of matrices. But in LLaVA 1.6, it's a multi-layer perceptron. In a multi-layer perceptron, you have a linear layer and you also have an activation layer, which will use an activation function that will be either a SILU or GELU, but you'll have that exponential type behavior where things will kind of round up to 0 or to very large numbers, depending on the input. And using that multi-layer perceptron, it's a more dense layer, so it can contain more information and it gives that activation type performance. So basically, by putting in a more complex adapter, they're able to improve their performance and improve the compatibility between the language model and between image model. Now, there's one other model I'll briefly touch on, which is called IDEFICS. The IDEFICS model is a little bit different than the LLaVA type models because it uses a Flamingo architecture, which I'll briefly show you a diagram of in a second. And also the training is different. It doesn't use synthetic instruction fine-tuning. Instead, it trains on multi-image documents. So very long documents that have multiple images with text interspersed between them. We can actually head over and take a look here at the Flamingo paper, which was one of the original multimodal papers. And the architecture used in Flamingo is the same as the one used by IDEFICS. What's unique about IDEFICS is that Dataset, which is the long document multi-image dataset. It's actually called Obelix. So these are all names from Asterix and Obelix, IDEFICS being the dog. And here you have the image of how Flamingo is architected. It's somewhat similar to LLaVA. You still have a vision encoder, this time for each of the images. And you have the perceiver resampler, which really can just, the perceiver resampler you can think of as the adapter. So also not too much change there. However, rather than feeding the vectors from the perceiver resampler or the adapter, rather than feeding that in the same way as vectors representing text, instead, these vectors are injected in parallel to each of the layers within the language model. So here, if you have, say, 12 layers within the language model transformer, these vectors from the adapters are being injected in parallel. And that's different than just injecting them once at the bottom. It's different because it adds in extra parameters. You now need to add in extra cross attention between the text and the image vectors within each layer, which means that when you start off with a LLaMA 7B model, it actually turns into a 9B model when you allow for these added parameters within each layer. And then the 70B model that the large IDEFICS model is based on becomes an 80B model. And the reason it doesn't become a bigger, like say a 90B model, is because they don't include the injection within every layer. I think it's once every 7 or every 8 layers. And that allows them to reduce the total number of parameters. But basically, I think the way the architectures are evolving is more towards the simpler LLaVA architecture, because if you consider the vectors going in right at the bottom, actually that information will propagate through all of the layers. And so whether you really need to inject at each of these points is kind of questionable, considering, as I said, the information still will get in through the bottom, through the adapter. And then because you're fine-tuning the whole model, it's as though you're allowing the model to adapt in any case. So you're achieving the effect of adding in these extra cross-attention layers here. You can check out the IDEFICS model for yourself on Hugging Face. It also runs with a version of text generation inference, which is quite interesting because as of yet, there are not great inference options available for these multimodal models. I do fine-tune the IDEFICS model, and it's included in the Advanced Vision repository. So if you do purchase access to that repo, you can check it out for yourself, because in this video, I'm going to focus on fine-tuning LLaVA 1.6, which we'll get to right now. I'm now going to use the Advanced Vision repository and the scripts within to prepare a data set for fine-tuning a vision and text model, and then fine-tune and evaluate the performance of that fine-tuned model. Now, you can purchase access to this repo at trelis.com, but I'll also provide enough information in the rest of this video so you can follow along if you want to take the steps manually by yourself. In the repo, there are 2 folders, one for data preparation and one for fine-tuning. So I'm going to clone that repo. I've got it opened up here in VS Code, and I'm going to start off in the data prep repository. Now, my goal here is to fine-tune a model to recognize chess pieces. So what I've done is take photographs of different chess pieces as my training data set, and then I've taken other photographs of combinations of chess pieces as my test set. So we can take a look here. It's public repo, chess pieces, and you can check out the train split. For example, here's a white rook, and you can see I've paired it with a caption that describes the piece. Here you can see a knight and a bishop. The caption is a white knight with a white bishop behind and part of a white pawn in the foreground. So actually you can see the white pawn here in the foreground. So I've got quite a small data set, just 48 rows. I think this is insufficient if you want to get very high performance, but it's still interesting because it will show us what kind of performance you get even with this small data set. Now let's take a look at the test split. Here I have combinations of pieces. So for example, I have a black rook, a black bishop and a white bishop all standing together. And I have this example here with a black knight and a white rook. So these are the photographs that I'm going to use when running an evaluation on my model, which I'll be doing as the training progresses to check that I'm not overfitting. And we'll also use them to show some manual performance evaluation examples once the model has been trained. To generate this data set, I simply took photographs using my phone. They are in HEIC format. So I put them all within the data folder here. And then I ran a script called HEIC to JPEG. So this simply converts my images into a JPEG format, and it also named them so that they have the prefix of chess pieces. So you can see here all the JPEG files. The next thing I did was run the create captions file. This gave me a template CSV file for the captions. And then I made 2 versions of that captions file, one for training and one for test. And you can see here, the captions file automatically had the list of all the images in it, and I just had to manually write in the captions that are required. So here you can see my train captions, and here are my 3 test captions. And then running the create HF dataset, I was able to convert this into a Hugging Face type dataset and push it up to the hub. So I was able to show you the dataset loaded as it is here. And once it's on the hub, we'll be able to download it in their fine-tuning script in order to run that training. After the dataset is ready, the next step is to move on to fine-tuning. And I know the font is small on the screen here, but there are folders for each of the models. So there's a fine-tuning notebook for IDEFICS, actually for the 9B and the 80B model. Then there's a folder for LLaVA 1.5. There's a folder for LLaVA 1.6, the 7B models based on Mistral, and then one for the 34B model. So we're going to take a look at both the 7B and the 34B models. And to do that, I'm going to open them up in Jupyter Notebook. When I do fine-tuning, I don't have enough VRAM on my laptop to do the fine-tuning, so I typically will rent a server using something like RunPod or VastAI. So let me just show you that exact setup. I'll show you for the 7B model and also for fine-tuning the 34B model. So one way that you can choose is to use RunPod. And if you go to this public repository, the Trelis Research Install Guides, you'll find a script, or rather a markdown file called LLM Notebook Setup, and you'll see some one-click templates for doing fine-tuning. So what I'm going to do is click this RunPod one-click template, and this is going to give me a CUDA 12.1 Docker image, and it's a fine-tuning notebook by Trelis. And if you're going to fine-tune the 7B model, I recommend choosing an A6000, which will give 48 gigabytes of RAM. I'm going to fine-tune in full 16-bit precision. The support is not, the script is not supporting 4-bit or 8-bit fine-tuning just yet. That would allow you to greatly reduce the amount of VRAM you use. So for now, with a 7B model, I would choose one of these. And actually, if you want to fine-tune the 34B model, I found that I needed 300 gigabytes of VRAM to fine-tune in 16-bit. So I actually used 8. I used 8 of these for that, but probably you could get away with 6 or maybe 7. So I'll click on deploy and then continue. And once that's deployed, you'll be able to go ahead and open up the Jupyter Notebook. Here I am in Jupyter with the LLaVA 1.6 fine-tuning notebook. This is for the 7B model. And so I'm going to take you through this script step by step. First off, we have the installation of the files. We're going to be fine-tuning using transformers from Hugging Face, so we'll install that. We'll also install bits and bytes, although I'm going to fine-tune in 16-bit, so I won't be using quantization in this example. As per my recent videos, I like setting this environment variable. This allows you for very quick downloads and uploads. The Hugging Face Hub enable HF transfer. And for that to work, you also need to have installed HF transfer, which is shown right here. Next, I'm going to clone the LLaVA repo. So I'm directly cloning from GitHub. And there are a few changes that already at this point I need to make to the scripts in order to get the best form of training. Basically, there are 2 things that need to happen. The first is I need to convert the script for loading the model to be 16-bit, but I need it to be brain float, B float, rather than float 16. Now, the reason for this is that LLaVA, it can be tuned in 32 bits, which requires a lot of memory, but the training is stable. If you try and train in float 16, often the training becomes unstable because of a lack of precision. Now, numbers are represented in digital format. There are a certain number of bits allocated to the exponent and a certain number of bits allocated to the precision. And what brain float or B float as a data type does is it uses the same number of bits for the exponent and greatly squeezes down the number of bits for precision. And so brain float basically is able to cover the same range of numbers as float 32. And so it's able to maintain the stability. Now, not every GPU supports brain float, only the Ampere architectures like an A6000, an A100, a H100. So if you're using an older GPU like a T4, then you're going to be forced to train in float 32 because float 16 which has a smaller number of bytes used for the exponent, is going to cover less of a dynamic range and it's not going to be as stable. So there are a few changes that we need to make in the loading script. The loading script that we're going to use is this one here, which is load pre-trained model. So I've just run this cell here to clone, and inside it, within the LLaVA folder, within the model folder, you will see a builder.py script. So I'm going to open up the builder.py, and if you search within this script, which is the script to load the model, you can just search for float16. You'll see that there are 5 instances of where the model is being loaded in float16, and those all need to be replaced with bfloat16. And that's to ensure that the model is loaded in bfloat and not in float, so that we can both keep the memory reasonably compact, but also keep the training stable. Now, there's one other change as well, which is when the vision encoder is being loaded, that's called the vision tower. We'll see it later in the modules. Right down here, we have the vision tower. And you can see as the code is structured, if the device map is not auto, you can see that the vision tower is going to be moved to the device, which will be CUDA, so the GPU, and the data type is going to be float16. Now that will be updated to bfloat16, but there is an issue because often the model can be loaded and this line of code isn't triggered. So we basically need to adjust this code so that it's always moved to being bfloat16, and so that it's never loaded in either float32 or float16. And I've basically automated that with this script here. So what I do is I search for a pattern, that's the vision tower piece, and I replace it with a pattern that forces the model to be loaded in bfloat16. And then furthermore, I replace all of the instances of float16 with bfloat16 throughout the script. And so I've run the script here to replace the vision tower component. And then I run the script that will search for the float16 pattern, provided it doesn't have a B before it, and replace that with bfloat as well. Now, just to note that you can leave the vision tower in float32 and the training will generally still work, but it will reduce your VRAM a little bit if you replace it with bfloat. Okay, so next, after we have cloned the LLaVA repo, made those adjustments for bfloat, and then we're going to CD into the LLaVA directory and make the installations that are recommended by the LLaVA repository itself. And once that is done, we can move on to loading the model. So here we're going to set the device on which we load the model as CUDA, and we're going to select a model that we want to load. And so here we have a selection of models. You can load Mistral 7B, Vicuña. You can load the 34B model, which I'll show you in a moment. Now, next up, we load not just the model, but also the tokenizer, the model, the image processor, and the context length. So we're going to load all of these at once using the model path that we've specified above. We're going to use flash attention to speed up fine tuning. And we're going to set the cache directory to just be empty, which means it will download the model to the directory that we're currently in. So that will download the model quite fast thanks to HF transfer. And after that, we should have the model getting loaded onto the GPU. Now, notice that there is this error and warning that is still unresolved when we're loading the v1.6 LLaVA models, but everything should still work fine despite those errors. Next up, we're going to move to examining the modules. So here, you can also optionally examine the model or the processor, but I like to check that there are no modules that are not in bfloat16. So I run this script here and I'm checking through all the modules to see that there are none that are in float32. And indeed, because there's none listed, we know that all the modules are in bfloat16. Next, we're going to move to inference, and we're going to use some inference code that's, again, based on the code recommended in the LLaVA repository. There's an evaluation function you can check out within the LLaVA folder. And what we're going to do is first create a prompt. The prompt needs to be set up with a combination of the image and with the text itself. And it needs to be prepared in a specific format. And that format for the conversation will depend on the model type. So depending on whether it's a Llama 2 base, a Mistral base, a 34B base, or an MPT base, you're going to need to have a different chat template. So that's what this is handling here. We have a function that will process and prepare images, which itself calls a function to load images. So here we have the load images function. And then we will wrap all of this in a function called eval model, which will take in a tokenizer, a model, an image processor, context length, the image file that we want to ask the question about, the query, this is a text question, the model name, and also some parameters like the temperature, the number of beams, the max new tokens, which are set to default values here. So within this eval model, what's happening is the prompt is being prepared and the inputs then, so the PyTorch tensors are being prepared using the tokenizer. And then we're calling the model.generate function with the images tensor, with the images size. We're also including the temperature and the max new tokens, whether to use caching for inference as well. And this finally gives us our output set of tensors, which is decoded using the tokenizer to give us the final printed outputs, which are the printed output tokens. So with that all done, we can run a quick example, and we're going to run an example on that night and rook image, which I've uploaded to a public URL. So running that, we can pass in the image and ask, what do you see in this picture? And here we have a picture of the knight and the rook. And the question is what you see in this picture. Remember, this is the 7B LLaVA 1.6 model. The image shows a chessboard with a few pieces on it. There's a rook on the A1 square, a knight on the B1 square, and a pawn on the C1 square. And the pieces appear to be made of wood, and the chessboard has a light colored surface. Now you can see there are some pad tokens that are appearing here. That's because I've used a patched model, patched version of this model, which adds in pad tokens. I actually think that is best not done. So if you are going to rerun this script, rather than using the patched model here, which adds in padding tokens, I recommend just using the base model here, which doesn't display those issues. Okay, so we have a quick example, and you can see that the model is recognizing that it's chess, but it's telling us that the pieces are on certain squares, which doesn't make any sense. And it's seeing the knight and it's seeing the rook. But as I said, it's not exactly understanding where they're standing. So next, we're going to load the fine-tuning data set. So we need to define a function to tokenize and create the labels. So we're taking in a batch of data, which has images and prompts. And the prompt is always going to be the same. It's going to be, what do you see in this picture? So we're going to tokenize the conversations with the caption, which is the answer. So we're going to use the caption in the data set, the caption here. That's going to be the response. And so we're going to need to tokenize the inputs without the response, and then we'll tokenize the full inputs with the query and the caption as well. And the reason for that is because we're going to focus the loss. When we calculate the loss and backpropagate, we're going to focus just on the captions, which are the outputs, and we're going to penalize the model and backpropagate on that basis. We're not going to penalize on the full sequence of tokens that are put into the model. So with this, we've got a function that allows us to set up tokenized versions of the full input, including the captions, and also creates an attention mask here, and it will include a loss mask within the labels. So just to make a specific comment on that, the labels are the targets. So when we generate a predicted token, let's say the predicted token is hello, we're going to compare that to what it should have been. And what it should have been is going to be a label. And the way we get that label is by just taking the inputs and using the input and shifting by 1. Now, the shifting by 1 is automatically done by the trainer. So all we need to do to get a list of targets is to copy the inputs and copy them over to the labels. And once we have that set of labels, which is just a copy of the inputs, we're going to convert some of those labels to be ignored. So we want to ignore the labels that are towards the start, and we don't want to ignore the labels that correspond to the caption. And you'll see this more clearly when I show a printed example of some data. So I've run this here and prepared the data set. And next up, we're going to set up LoRA. So to set up LoRA, the low rank adaptation, we're going to fine tune not the model itself, but rather a low rank representation of the model. We're first going to print the model to see all of the layers. Within the model, we have first off the Mistral model. So we have the attention layers here. You can see of Mistral, and there are 32 layers from 0 to 31. You can see the multi-layer perceptron layers of Mistral as well. And you can see the input layer norm and the post-attention layer norm. And now you can see the vision tower. So this is the vision model here. It's a clip encoder. And you can see the embeddings. And then you can see within the encoder itself, it's 24 layers. And it also has got attention, so KVQ. And it's also got linear layers. So we've got the attention, KVQ. And then we have the clip linear layers. So here we have the multi-layer perceptrons, which we've got FC1 and FC2. And then last of all, we've got this, the projector. And the projector is the adapter I talked about. You can see that it has a linear layer here. It has a GELU, which is an activation function, and it has a linear layer here. So this is the adapter I talked about back in the presentation. We can just show it very quickly. This adapter here. So this is represented within the code right here as the projector. So you can see each of the elements. We've got that adapter. Here we've got the clip encoder. And up here we've got the Mistral model itself. And what we want to fine tune is we want to fine tune the attention layers. We want to fine tune the multi-layer perceptrons. And by the way, when we specify QProj, it's going to create a LoRa adapter also for QProj in the vision encoder. So we're going to fine tune the attention and the MLP, the multi-layer perceptrons, in both the language model and the vision encoder. And we can also optionally train the projector itself if we want to train that adapter. So here you can see I've specified the attention layers. I've specified the multi-layer perceptrons. And then here, MN projector, that's for fine-tuning the adapter. And when we get that LoRa model and print the parameters, you can see there's about 0.4% of the total parameters, including now the LoRa parameters that are trainable. So we're really just training a very small subset, but they are low-rank adapters. So they're going to get a nicely smoothed update to the overall model's performance. Before going further to training, let me just quickly recap. So we've done the installation, we've loaded the model, we've done inference, or rather we've set up the functions that will allow us to run inference before and after training. We've set up the fine-tuning data set. We have applied LoRa adapters to the model. So we have the adapters ready to train. We'll freeze the main model, train those smaller adapters, and then merge back onto the main model. And now we're going to run evaluation before training, and then run training, and then run evaluation after training. Now, I've reloaded the script with the base LLaVA 1.67b model, so we don't have the issue with the patched version I've loaded. And now we're going to run evaluation across each of the samples in the test data set, of which there are 3. So we run that. First, we have a bishop and a knight. And you can see the answer before training is on the left, there's a rook, and on the right is a pawn. So that's not quite right. The next example is of 2 bishops and a rook. And the answer is the image shows a wooden chess set. On the wooden table, there are 3 pieces, a king, a queen, and a rook. So not quite right either. And the third example is a rook and a knight. And the model sees there's a rook on the A1 square, a knight on the B1 square, and a pawn on the C1 square. So it's seeing squares, even though the pieces are just on a table, not on a chessboard. So let's see if we can improve performance now by running training. For training, we're going to use the standard Hugging Face trainer. So we will set the BF16 parameter to true. That means we're using brain float 16. We're not using FP16, which would cause instability. A learning rate of 1E-4. We're going to train for 3 epochs here, and we'll keep an eye on the eval loss, make sure it's not rising to indicate overfitting. We'll use a train and an eval data set. And the batch size we'll use will be 4 for the training, and eval we'll use a batch size of 6, which is really not relevant because our max batch size is only 3. So you could just reduce that down to 3. And now we'll run the training. It will automatically connect weights and biases, which you'll have to sign in for. And just looking at the training loss, you can see that it's dropping. It does jump about a little bit here at the end, but I know because the validation loss is dropping, that the training is relatively stable. And as you can see, it looks like I probably could train a little bit more, although the loss is maybe asymptoting a tiny bit, but certainly seems like there's room to train a little more. Nonetheless, let's take a look at the results of evaluation after training. To evaluate after training, we'll run the very similar script as before. We'll iterate through each of the 3 examples. So here's the first one. We have a bishop and a knight, and the answer is a white king and white queen. So the colors are correct, but the pieces are wrong. In the second case here, what you see, we have a rook, a bishop, and a bishop. And the answer is a black king, a black queen, and a white king. So the colors again are correct, but the pieces are not correct. And in the last case, we have a rook and a knight. And the answer is a black knight and a white rook. So in this case, it's getting the answer correct. Now again, this is the 7B model. I'm going to show you the 34B model just in a moment, but it gives you a sense for the kind of performance to expect, albeit on a very small data set. And I think using a larger data set, taking images from different angles of the pieces to give more perspectives would allow us to improve performance, perhaps combined with training for 1 or 2 more epochs until we see that eval loss starting to rise again. Before wrapping up, I want to clarify 4 different points. The first is around the amount of VRAM that you need. I find that if running the version 1.6 Mistral model, I actually need 3 A6000s. So I need over 100 gigabytes of VRAM, and 2 A6000s is not enough to load and fine tune in 16 bits. If you want to do the 34B model, that's going to take over 300 gigabytes of VRAM. And for that, I used 8 A6000s, but I think probably 7 is enough. The second point I want to clarify is around tokenization. Here are the tokens from a row of training data. And what I can do here is copy paste this and put it into a vector just for demonstration purposes. And I'm going to take out the -200 entry in it here. And then I'm going to tokenize or decode this and print the output. And this shows us what that row of data represents. It's the begin of sequence token. Then there's this instruction start token. Then the prompt, what you see in this picture. Then the instruction end token. And then the caption, which is 1 black rook. And after that, there's the end of sequence token, followed by padding tokens, which are the UNC token or the unknown token in this case. Now, the reason I deleted the -200 is because this is used to represent the image itself. In fact, this is actually the image token index, so -200, and that's how LLaVA is representing the image token within the model. So that's why when we see the first row of data like this, it actually corresponds to this prompt with the image token inserted right here. And I should note that there's a custom tokenizer being used, this tokenizer image token, which handles that special token. So if you just use a normal tokenizer, that's going to cause issues for doing inference or for doing fine-tuning on a LLaVA model. The third point I want to highlight is around the tensors that are produced to represent the images. You can see here that we have a batch, and this is a batch of 4 rows of data. And here is the tensor representing the image. So it first starts with 4 because there are 4 rows within this. And then working backwards, you can see 336, 336. This is the number of pixels. And this corresponds to the input size for the clip vision encoder, which is 336 by 336 pixels. Then the number 3 represents red, green, and blue. So they're the 3 colors that together represent the color of a given pixel. So there's this further dimension here, 5. And this 5 means that there are multiple representations of the same image being used. So what LLaVA is doing in v1.6 is it's representing the image as a reduced version of the original image, but then it's also calculating patches for that image. So it might have one main image, and then it's got 4 patches that are superimposed over parts of that image. And this is beneficial because it allows the model to see the image in 5 different ways, one in a whole version, and then 4 other patches. And so that's why we actually have 4 rows, but then for each row, that image is represented 5 times by 4 patches plus a big patch. And then we have 3 RGB, red, green, blue, and then we have the pixels for each of those 5 images. And that's it for this very first primer from Trelis Research on vision models. This is going to advance rapidly with models that support even larger images and using more performant language models there as the building blocks. So I'm excited where this can go. And I think it allows for a lot of applications where you can take a data set of images, whether that be medical, whether that be sports or otherwise, and use them to fine-tune models that are going to be able to be used in conversational format. As usual, let me know your comments down below. Cheers.